Let's look at Friedel Crafts acylation. It's similar to the alkylation, but the reagents are different. So top one, how do you see normally, but I'm going to write it different in the bottom one. So see, I flip the acyl chloride and I put the catalyst in on the arrow, and then HCl we marked, and that's the byproduct. So you remove the HCl, and what is left over is C double bond OR and the phenyl group. So you put them together. So that's an easy way for a cheat sheet. What is the bottom layer? So make sure the byproduct, pay attention, and also pay attention to the catalyst. It should be regenerated. So that's how we're gonna look at it, and all the details in one line, one reaction, you have it. So not the top one, the bottom one. More details. Now we do have an electrophile on the carbon double bond O carbon, and we have a nucleophile on the pi bond of the benzene, and this will react on the aromatic substitution because of the hydrogen goes away. So that's how you get the EAS, electrophilic aromatic substitution. Let's look at a little bit more about the catalytic process. Now here, even though I mentioned an electrophile, this will be activated with the catalyst, and then later catalyst will be released. Let's look at the catalyst, the Lewis acid. So aluminum chloride is a good one, aluminum trichloride, right? And then this one will donate, any of these lone pair will donate to the electron deficient aluminum, and the C to Cl bond will be broken. Now you generate RC double bond O positive, which is, we call the acyl ion, ium for the plus, and typical aluminum tetrachlorate, negative ion there, right? And acyl ium for the positive. Remember that one. This cation actually has resonance stability as well. I will show you in a moment. Here I drew it with the 120-degree angle. See what happens in a moment. Okay. Now, so let's redraw in a simplified version for the catalytic process. And you have the acyl chloride, right? And then aluminum chloride comes near, electron deficient, it pulls out the pair of electrons from the acyl chloride, and it will make this CH3C double bond O, which is the acylium, or you can call this an acetylium as well. And then aluminum tetrachloro negative ion sitting there, it's a counter ion, it should be nearby. Right now, this lone pair on the oxygen will be it's the activated electrophile actually. So this will be making the resonance structure. So look at the first, like, okay, let's put the benzene ring. I'm highlighting the 2 dots for the nucleophile, and I'm highlighting the hydrogen which will be replaced, right? Now you get this one. So how do we get this triple bond O positive on the carbon? Because carbon prefers the positive than the oxygen, right? So it's 180 degree. This is the resonance structure between the two, right? So you should actually be having this acylium 180 degree linear version, and because carbon has a plus, right? So now nucleophile will attack the electrophilic carbon, and the pi bond opens up to the oxygen. So that's how it should work if you're looking at the mechanism details. Now I can redraw this benzene, and then what we did is we donate 1 electron to the carbon, actually the pair, and that make the new bond, and then the C double bond OCH3, the green one, that's the new piece came in. Now we generated a positive here on the benzene ring. So this is a sigma complex. It's not aromatic anymore. Now this one should show resonance stability, right? Now I'm going to write the negative ion by the side, that's just the counter ion sitting there. Now sigma complex should show typically like in the alkylation, we will have 3 different positive sigma complexes, right? And we can also get the product out of these two, because aluminum tetrachloroanion will deprotonate the benzene ring, and then you end up with the final product. So the acylation took place, right? So that's a good way to look at it. Now, just for details of the resonance structure, so I can show the first one we generated, and we should have the carbonyl functionality there, and then you have the positive, right? Now what you do in one direction, each time pi bond moves to the positive charge and then makes a new pi bond, and the positive charge moves one bond away. So you keep doing that until you come back to the original structure, right? And that's how you get the three different resonance structures. So it's a good idea to go in one direction, right? So again, you draw that one, so you get no, actually we're going to redraw this one here. Yes, get rid of the final product for now. We can put it back. Need some more space here. So now the positive moved onto the top of the benzene ring, and then you have the other pi bonds we didn't touch, the hydrogen still there, and the carbonyl functionality still there, right? The green one. So now we have gone through all the three resonance structures. You can show it with the square bracket and 1/3 of the possibility of each. There's no priority on each, 33% each. And then we pick up this proton because of the basic nature using to deprotonate the hydrogen here. Now you recreate the aromaticity within the benzene ring, and you have the acyl group sitting on it, and the hydrogen is gone as HCl actually. So I can still show HCl and aluminum trichloride together, aluminum chloride, and you can separate them easily. That way you have the byproduct, you have regenerated the catalyst aluminum chloride, right? Now, so we also can look at what's the possibilities, just like in the alkylation. The acyl group is any acyl halide is fine. That means acetyl chloride, acetyl bromides, normally, typically those are the ones. And the X would be mostly Cl and Br, right? Then R group could be vary CH3, ethyl, methyl, propyl, butyl, and so on. Now, not only that, you can also take acid anhydrides. So it could be acetic anhydride, propionic anhydride, and so on, right? So you can get anhydrides. So how do you see simplified version? This part is basically the halide, okay?